full charge. And so we're going to have 3 resonance forms for this. Other resonance form. So this is octet. Now, this would be an sp2 sigma, and a pp pi. So this would be series 1. Series 2, we can try to make 1 pd pi in addition to the pp pi. And that's going to lower the formal charge on sulfur by 1. But it's also going to expand the octet. So we got 2, 4, 6, 8, 10 electrons now around it. So the formal charges drop down. Plus the resonance forms for this. So we have top right, and then we can have top left, double bond. And then we can have left right, with a double bond. So we can draw the resonance forms for this. Or we can expand the octet fully and get rid of that formal charge entirely. Here they're going to be no formal charges, but we're going to have 2 pd pi bonds because we run out of the pp pi bonds here. We can only form 1. This is sp2. Forming 2 pd pi bonds in a trigonal planar type arrangements. It depends on how much d orbital contribution there is. This is going to have the most because we're going to have 2 pd pi bonds. This is going to have the least d orbital participation. So the end conclusion at chapter 11 is that it's thought that there's very little d orbital participation in the expanded octet. And it's thought that because the d orbitals are in the next shell. You know, even though they're 3, n equals 3, so we have the 3s and the 3p in the 3rd shell, we have the 3d in the 4th shell. And the 3d are in the 4th shell, that's a bit too high of a reach. But your book still does it. And so your book hasn't come up with a full conclusion yet. They're saying this is based on 1 study, so more studies need to be done. Our book, the publication date is a little bit old. You know what edition? This is the 11th edition, and it was published when? In 2019, is that correct? Well, anyway, I looked at some more recent studies, but still these more recent studies, which was 2022, I think it is, some of these more recent studies are saying don't expand the octet. Keep it like this. But regardless, if we expand the octet or we don't expand the octet, the true structure is going to be the hybrid of these. And so it depends on how much D. It says very little D. Does very little D mean 0 D participation or just very little D participation? And so that's not entirely clear how much D unless you go to the original paper and take a look. So there. But then I looked at where the original paper was published. The original paper was published in the Journal of Chemical Education, which is different than if it were published in, let's say, one of the premier chemistry journal that focuses just on chemistry is the Journal of the American Chemical Society, also known as JACS, JACS, Journal of American Chemical Society. So that's where you'd expect to find it in either JACS or Science Magazine. Science Magazine or Nature. Science and Nature are a little higher level, but they look at all of them. So you'd expect to find this in JACS too. And so what we can conclude here is we just conclude that, you know, the is some hybrid. So we'll have a hybrid structure of this, hybrid structure of this, and this has no hybrid. And then we'll hybridize all potential structures here and come up with a hybrid. And the hybrid's not going to be an even hybrid. It depends on how much. If the amount of d orbital participation is minimal, then it's mostly series 1. If there's a little bit more d, then 2, possibly 3. I, in particular, don't like this one because, this is 2 pd pi bonds in a 120 orientation, but the d orbital is at 90 degrees. And so this is going to result in very poor orbital overlap. We want the lobes to overlap straight on. When you look at how most people write sulfur trioxide, this is not sulfite, this is sulfur trioxide. They do it with 3 double bonds here. Sulfur trioxide. You take a look at most of the images for sulfur trioxide, they're all 3 double bonds. And so what they did was they went ahead and expanded the octet to get rid of the formal charge. Some people will do a series of structures, like here. This is normally the way I do it. Series 1, octet, 2 partially expanded, 3 fully expanded. Then do some kind of hybrid of that. But this is the, 2-pronged method. We got to see, how much D, and then figure out which one, because it's too hard to predict based on what we know. 3 double bonds, yeah. 3 double bonds.
But for that problem, it gives like a list of like 5 or 6. So should we do, the series for each one? And like some of them are pretty complicated.
What was
Chapter 10, number 6.
So this is just asking which ones that do not. We could say, rather than saying do not, that potentially do not obey the octet rule. So if we say that potentially do not obey the octet rule, then BOH3 would be one, because boron is less than an octet. Silicon hexa, this is an anion here, so this would definitely potentially not. I mean, we could have it as an octet. There's 2 ways of looking at it. That's so 3, and so we don't have to draw the whole thing. So it's not asking you to draw; it's just saying which ones potentially do not. So something like phosphate may or may not, depending if you draw one, double bond to get rid of the formal charge. So we could go like that. And so if it has the potential to expand the octet and lower the formal charge, then that could potentially violate the octet rule. More data needs to be taken. It would be better if there was a definitive answer, and then we can do it that way. But this is valence bond theory. We don't have to worry about this in MO theory. In MO theory, we're going to get a structure. The structure is going to have 3 equivalent sulfur-oxygen bonds. We don't have to do this. This is one of the reasons or failings of the valence bond. In MO theory, we'll just get the hybrid, the end result after all this. Just get that. And so it's a different way of approaching it. And so this is probably why a lot, because, from the standpoint of valence bond, if valence bond were the ultimate theoretical description of bonding, then we need more. For sure, we need to figure out, well, how much D, if any, participates. But since this is not, and the MO calculations, this is why they say there's a conflict, because the MO calculations, when they mix the orbitals, with LCAO, there's very little D that gets mixed in the LCAO. And so this is why. But this is a slightly different case though, because we have, different hybridizations, sp3 and then sp3d and sp3d2. And so there's two ways we do D. One is expanded octet. Two ways of expanding the octet. One is to have more bonds, more single bonds. That's sp3d and sp3d2, where we can have 5 things bonded and 6 things bonded. 4 things bonded would give us an octet. Or we could have this PD pi bond, expanding the octet. Now the PD pi bond is a little different, and so it's not as trouble. So unfortunately, I can't give you a better answer, but either way you say this, if you say yes, okay, that's fine. If you say no, okay, that's fine too. I'll take or accept either. For lab A, yeah, you'll have to turn in your Lewis structures. You're supposed to draw them, the shapes of them, I think. But otherwise, you have them all checked off, so you don't need to turn anything in. If you didn't get them checked off, then you'll have to turn them in. Yeah, you should draw them, Yeah, and you should draw them, and so I'll just check off because if I draw it on the board, but you draw it on paper, sometimes they don't match the structures how they're drawn, and so I want to see it. Even though I wrote it on the board, not everybody copies it in the same way, and so I just got to make sure it's correct. Yeah, you can check them off also. Okay, other questions? All right, I forgot to post chapter 16 homework. Eventually did get it up. The chapter 16 homework is on Canvas now. It's just number 65, starting there, molecular structure and acid-base behavior. This is just doing the stuff that we did earlier. Here we have, is it ortho, meta, para? Or meta, ortho, para? No. Ortho, meta, para. And so which one is stronger base, that kind of stuff. So we were doing that last week. But I also tacked on this one, Lewis, acids and bases. So it's been a while since I talked about Lewis acids and bases. So let me just go through some of these problems, just to refresh your memory. And so let's take a look at the first one, 71A. Yeah, each time you exhale, you're exhaling what gas? CO2. And what can happen is that CO2 can actually react with water. In other words, contaminate water. You might have pure water, but if you're exhaling next to pure water, do you know what's going to happen is that CO2 can potentially contaminate your water, and that would be a Lewis acid-base reaction. We've talked about this one a long time ago, but might be. When we do Lewis acid-base reactions, we usually write out the Lewis structures and when we analyze the molecules. And a Lewis base is what? Electron pair donor. And when we look at for bases, we look for negative charge. We want negative charge or negative charge density. So the more negative it is, the better electron pair donor it's going to be because we need more electron rich. So when we look at this, oxygen is more electronegative than carbon. So it's going to polarize that bond. Carbon's going to be delta plus the bond. So this is Lewis base here. These two oxygens. And a Lewis acid is what? Electron pair acceptor. And so CO2 has both acid site potentially. Because if this accepts an electron pair, then we have a problem. That means we're going to have 5 electron pairs. Is it possible to expand the octet on carbon? It's actually not possible. You know, the whole idea of getting 5 electron pairs is we have to utilize d orbitals. And the nearest d orbitals for carbon will be 3d because it's going to be in the 2d. 3d for sure is too far away in terms of energy. And so if there was such a thing as 2d, then maybe the 2d orbitals are forbidden. And so if this carbon were to accept an electron pair, something has to leave. And that would be the pi. And so something can leave. The pi bonding electron pair can leave for this oxygen. So we have acid site here, carbon, and base sites, oxygen. And then we have water over here. If we have water over here, we have a potential electron pair donor, this oxygen, which is be delta minus, so that's good. This is delta plus, this is delta plus. So we have 2 choices. Choice 1, this base site oxygen attacks this acid. So if this lone pair here attacks a hydrogen, then these bonding pair can leave. So we bond this hydrogen here, and then we'd end up with hydroxide. That's one possibility. Or another possibility is if this base here on water attacks this acid on oxygen. That's the other possibility, and that's actually the possibility that reacts in this case. And so here it is. This would be our Lewis base, negative charge density, lone pair, attacking our Lewis acid, positive charge density. And we got to make room. But we can make room because if this lone pair comes to carbon, then we can kick out the pi bonding electrons, make those a lone pair. And so we don't exceed the octet. And so it turns out in this particular reaction, CO2 is the acid, water is the base. This is just the first step. That's all we're going to look at. This is just the first step here. And so we'll just say, etc. And eventually we have carbonic acid over here. Mm-hmm.
So one of the hydrogens would be put to another oxygen. Is that true? So that one oxygen.
Yeah. Yeah. Right. What's going to happen is we're going to get what I call the intra means within, intramolecular proton transfer. So there's going to be an acid base. It's also a Lewis acid or Bronsted acid base reaction in which one of the oxygens will pluck a hydrogen. That would be the second step. And then we're at carbonic acid. We did this one a long time ago. So let's try another one. Let's try D, sulfide and sulfur trioxide. So if I use sulfide, we'll do the Lewis structure. So -2. This one cannot be a acid. This one's only a base, right? Because it's got lone pair, so it can donate one of its 4 lone pairs. It's got negative charge, so this is a good Lewis base. And then it's going to react with sulfur trioxide. Now, which structure for sulfur trioxide am I going to do? I'm just going to do the octet. The octet structure is not wrong. Not too many electrons, let me make sure. One, two, three, four, 5. Sulfur trioxide is neutral. So I'm going to try to draw this so it comes out neutral with not hat. How did I draw it?
Turn the top one and the double one.
Yeah, okay. Get rid of that. Yeah, I think I did that. 1, 2, 3, 4, plus 2. That was it. When we do this, we don't do the hybrid, we just pick one structure. That's going to be the easiest. Just pick a structure. Now, if I look at sulfur trioxide, and we just use this structure, then which of these bases will be the best? An oxygen with a negative charge or an oxygen with 0 charge? What would be a better base? Yeah, the negative charge. The weird thing is all these oxygens are exactly the same because really the true structure is the hybrid. But when we do this, we just pick one of these. This one would be better than this one. So it's not totally accurate, but it's all right. So sulfur trioxide has base sites, these oxygens, and it has an acid site. Where's the acid site? The acid site is sulfur. But if sulfur were to gain a pair of electrons, then it would exceed an octet. And so I'm going to not violate the octet rule. And so if it exceeds an octet, something has to leave. What leaves? Yeah, the double bonding electrons would have to leave. And so I don't want to exceed an octet. So what I'm going to do is I'm going to have this one. This is the base. This base is going to attack the acid here. But since I don't want to exceed an octet, I got to kick something out. And so what leaves are those pi bonding electrons here. And then we end up with this one, thiosulfate, S2O3. Let's do a side. Let's try to take a pretty good Lewis base, like hydroxide. Hydroxide is a pretty good Lewis base because this oxygen, negative charge, got a lone pair. We can donate one of its 3 lone pairs here. And let's try to get this to react with methane. What do you think the hydroxide will attack? Do you think it will attack the hydrogen or the carbon? Yeah, probably the hydrogen will attack. The reason is because this carbon, carbon has an electronegativity of 2.5, hydrogen has an electronegativity of 2.1. So carbon's more electronegative, meaning that the carbon's going to be delta minus. And so delta minus, is that going to be very good, a minus and a delta minus? No. And so it's going to be the hydrogen. Now, the delta minus and the delta plus are very small. I mean, we call this a non-polar bond. And so these are negligible. So let me put a little asterisk here, because the delta En here is only 0.4, which means it's fairly non-polar. And so these are kind of over-exaggerated. But nonetheless, it's probably going to be the hydrogen that gets attacked here. And so if the hydrogen gets attacked, then something's got to give. And so what gives? If that hydrogen gets attacked, then what goes, because the hydrogen can only form one bond. And so we got to get rid of this bond. And so this lone pair goes there. And we end up forming methide ion, a carbon with a lone pair in water. Is methide very stable? No, methide's very unstable. Very unstable. And so this is not a good Lewis acid. Methane is a very poor Lewis acid, whereas something like sulfur trioxide would be a much better Lewis acid. You know, we got this +2 charge and many things. So that brings us to number 72. Number 72A, these are getting more complex. And so what we'll do is we'll kind of look at what's happening here. So we'll go with SOI2. So I'm going to try to draw these without going through the full set of rules. SOI2 is neutral. So this is going to be -1, this is 0, 0, 1, 2, 3, 4, 5. So this will be +1. If I make a double bond here, I can get rid of the formal charge, but that would mean expanding the octet. And so what I'm going to do is I'm just going to leave it as an octet here. So when I look at this particular molecule, you know, it's a neutral molecule, but it does have a plus and a minus formal charge. Do you see what would be the best base atom in this? The oxygen. And then the best acid, sulfur. Now we're going to react it with barium sulfite. Now this is sulfur trioxide here. Sulfur trioxide is neutral, but sulfide is -2 anion. And barium sulfide is an ionic compound. And I don't like the way your book does Lewis structures for ionic compounds. For ionic compounds, we draw a lattice structure. And so let me try to draw the Lewis structure for sulfite. One, two, three, four, five. Yeah. Maybe something like this. I'm not going to expand the octet. We can expand the octet by 1 here. Get rid of the formal charge. I'm not going to do it. And then this is going to extend. You know, this is etc. Alternating. Now, you know, we have different options here. So this is a pretty good base. So this base here, the oxygen can attack. So for example, this base oxygen can attack this sulfur here. This one possibility. If this attacks that sulfur, then we got to get rid of something. What are we going to get rid of? Can we get rid of a lone pair? You know, we don't want to exceed an octet. So if this lone pair gets donated to that sulfur, then we have 2, 4, 6, 8, 10 expanded octet. We're not going to expand it. So we got to get rid of something. In the previous example, it was easy to get rid of because we just got rid of the pi bonding electrons, converted the pi bonding electrons into a lone pair. But in this example, we got to break something off. We can't break off a lone pair because is a lone pair stable by itself? No. And so what do we have to get rid of? An oxygen. And so if this base comes in to attack the sulfur, then one of these oxygens has got to go. We're going to be left with an oxide. Well, oxides are kind of reactive and unstable. What if this base, in terms of Lewis, we always think about the base attacking the acid. And the arrows are always drawn in that way. So what if one of these, now these are the same, what if one of these attacks this sulfur? Well, something's got to go. And what would that be? Yeah, so if this base comes over here and attacks this sulfur here, then we're not going to lose this lone pair, but maybe we'll lose this. And so what's going to happen is if this base attacks this sulfur, then this iodine has to leave, has to go. And so it's pretty much going to be leaving as what? So we're going to just say goodbye to this bond and goodbye to that atom, and we're going to be left with iodide. And so based on this, based on what forms, this has got to be it. So this oxygen comes over here, attacks, and then we lose that iodide. Well, we got to lose another iodide. We're going to lose both iodides. But what's going to happen is now we got this thing attached to that. And so what's going to happen is there's going to be more steps. The more steps would be this oxygen's got to go to that sulfur. In other words, this SO2 will break off, and the second iodide is going to come off. And so there's going to be subsequent steps. So this would be step one of a multi-step mechanism or process. We're not going to look at the whole multi-step because it can get complicated. But we can see how we can do this along the way. And so even though, this can act either as an acid or a base, in this particular reaction, this one is going to be the acid, and this one will be the base. Sometimes something like barium can actually react, as well. And so that's looking at this one, B. This is more of a Chem 1B type reaction. This HgCl3 minus is called a complex ion. HgCl4 minus is 2 minus complex ion. This one over here, ZnOH4 2 minus, this is a complex as well. And so let me do a side reaction here, and then we'll take a look. The formation of these complex ions. We did this before in lab, and that is, I don't know if anybody remembers this, but Pb2+, we can precipitate it using chloride. The metathesis reaction will form PbCl2 solid. And we get a white precipitate. However, if you add too much chloride, you know what happens? We did a reaction similar to this in lab. I think we did with hydroxide. If we add too much chloride, then what happens is it gets attacked even further. So what we end up with is the Lewis structure. This is an ionic lattice. There's a Lewis structure for ionic compounds. It's like this. And so here's one, what we call formula unit, and then it just alternates lead, chloride, lead, chloride, lead, chloride. Fill up that lattice. But what can happen is if you add too much chloride, we can have another Lewis acid-base reaction occur. And so the chloride comes in and attacks the lead here. And what forms is this. Now, this is kind of weird. because I went from an ionic lattice. Too much chloride is going to break this apart and dissolve the lattice. We're going to end up with PbCl3 minus. PbCl3 minus is all the complex anion, and this complex anion is actually aqueous, and so we break apart the lattice and form these. These complex ions, like this, are written with covalent bonds. This is a Lewis acid-base reaction in which chloride is the electron pair donor. Lead would be the electron pair acceptor, and this whole thing is going to be minus. Another chloride can come in here and attack the lead, but in this case, it doesn't happen. We stop here. If this were mercury, then another chloride can come in. So let's replace that lead in the center with mercury. If we replace that lead in the center with mercury, we have this. This is the trichloro. We call this, the name of this, you don't have to worry about the name of this until Chem 1B. Trichloroplumate 2. It's called the trichloroplumate. This one is called trichloromercurate ion, mercurate 2. But in this case, a fourth chloride is going to come in here and attack it. Here, nothing's going to have to leave. For these complexes, valence bond theory does not work. For complexes, we can only use molecular orbital theory. Valence bond theory fails. And so in this case, nothing has to leave. It doesn't have to obey the octet rule. In fact, we don't even think about the octet rule for these complexes. So we end up with this. And so this is our acid, this is our base here. I don't like the way the book does Lewis structures for ionic compounds. So for example, zinc hydroxide is an ionic compound, but the book draws this as a molecular compound. Not. And so I'm going to do this one since the book does it differently. I'm going to write the zinc and then hydroxide. What's going to happen is another 2 hydroxides can come to attack this. This is probably going to happen in multiple steps, like 2 steps, but to keep this kind of simple, we'll just do it in 1 step. And so the zinc is going to actually act as an acid. And then it's going to break apart the lattice. What I'm going to form is this. This is called tetrahydroxozincate 2. Ion. This is another example of a complex ion. Let's take a look at 75C as the next example here. (75C), the first molecules, kind of like an alcohol, except rather than having an H here, we have a hydrocarbon substituent. These are the ethyl substituent. In fact, we have two ethyls here. So this is called diethyl, and this kind of linkage of COC is called an ether. So this is diethyl ether. Diethyl ether, and then boron trifluoride. Boron trifluoride, this has less than an octet. So when I look at diethyl ether, what stands out more? Lewis base or Lewis acid? Base, yeah. We have electron pair donor, the oxygen. So this would be a base. This is negative charge density. And then we have these hydrogens, which would be the acid. The carbons are going to be slightly negative, although it's possible, it's possible those could be attacked, and then hydrogen has to leave. This is fairly non-polar. That'd be green. But this is going to be acid for sure. The fluorines could be potentially base, but those aren't very good. Fluorines doesn't want to share, so it's pretty poor. We end up with this attack. Here, nothing has to leave. Nothing has to leave because boron doesn't even have an octet. And so what we end up forming is something like this. So one of the lone pairs on oxygen is converted to a bonding pair. There's going to be some formal charge here. Formal charge on oxygen plus formal charge on boron is minus. This whole thing is neutral. This thing is called an adduct. It's a combination of Lewis acid and base. Now we can see some more addicts. This is from UCLA, I guess. Another Lewis acid base reaction. Nothing has to leave. But we do end up with a formal charge over there. Here's an attack here. When we attack, we usually think of attacking the hydrogens because those are going to be slightly positive, but the electronegativity difference is marginally different. And so typically this is thought of as a non-polar bond. If that's the case, then there's not really much of a charge, on it. And so if it did indeed attack carbon here, something's going to leave. We don't have any pi bonding electrons. The pi bonding electrons are perfect candidates for leaving. In this case, we're going to have too many bonds. We have 5 bonds around carbon. And so we have to either kick off an iodide, like we did over here, like in the previous reaction, or we'd have to kick off a hydride. Well, hydride versus iodide, iodide's a lot more stable than a hydride. Hydrides are quite reactive. And so in this case, we're going to lose the iodide here. It would just be a Lewis acid base reaction. In organic chemistry, they have all these additional categories. The additional category is called an SN2 reaction. And they look at the mechanism. Sometimes what happens is one of the groups leaves first, breaks off with the solvent. This is called SN1. It's all, the solvent's going to fluff it off. It's a Lewis acid base type reaction. So, hydroxide ion, Lewis base to form methanol. This is not an example of Lewis acid adduct. An adduct is just a combination, which is fine up here because we don't have to, nothing has to leave. But in this case, the whole atom has to leave as an ion. And so it's not an example of an adduct formation, but it is an example of Lewis acid base reaction. And organic chemists are going to have all these subcategories. Okay, this is an SN2 reaction. Because what has to give is one of the atoms that departs. They call the atom that departs a leaving group. And they have different, depends on how stable the leaving group is. Here, hydrogen doesn't make a good leaving group. Iodide makes a much better leaving group. In this particular reaction, nothing had to leave. But even when we have, let's say, pi bonding electron, if we have pi bonding pair that has to leave, then that's not a big deal. We aren't kicking off an atom to make room. Okay, here's another example of complex. This is a weird one. We have ammonia, which is a good Lewis base, attacking silver ions, which will be our Lewis acid, resulting in a complex in which two ammonias are actually covalently bonded to the silver. This is called diamine silver ion. Those are, again, are discussed in Chem 1B, so I wouldn't worry too much about them now. In this particular set of problems, you're just trying to identify which one's going to act as the acid, the acceptor, and which one's going to act as base. Okay, so I gave you a set of problems of this. They're posted on Canvas now. Let's go back to chapter 12. Where did I leave off on chapter 12? Were we looking at this graph?
No, I don't think we started.
We haven't started chapter 12?
Yeah, we haven't talked about IMFs.
Okay, we haven't talked about IMFs. Did we finish chapter 11? In chapter 12, we're looking at IMFs, intermolecular forces. Also, we're going to look at some liquid and solid properties, liquid, solid, and gas properties. And so, 12.1, we're going to look at intermolecular forces, IMFs. 12.2, some properties of liquids. 12.3, some properties of solids. 12.4, phase diagrams. 12.5, the nature of bonding in solids. 12.6, crystal structures. What lab are we doing tomorrow? Yeah. We're doing crystal structures. So tomorrow at the beginning of the class, I'm going to jump to crystal structures. We'll talk about those. 12.5 and 12.6 tomorrow. 12.7, just energy changes. When we convert solid to a liquid, it's melting. A liquid to gas is vaporization. We're going to look at the energy changes associated with that. So first, we're going to look at intermolecular forces, or IMFs. In this section, we'll examine the types of intermolecular forces known collectively as van der Waals forces. You remember van der Waals? Van der Waals equation? What was van der Waals equation? Van der Waals equation was back in chapter 6, gases. And Van der Waals equation described what? It was a modification to the ideal gas law to compensate for real gases. Two things that differentiate an ideal gas from a real gas. What were the two things?
So the two things that you can change to make it more ideal. So we're gonna-
Yeah, or two things that you can change to make it less ideal. Okay, temperature. Gases behave more ideally at high temperature or low temperature? At high temperature. The reason why gases behave more ideally at high temperature is because
molecules are moving faster, so
they're less likely to stick to one another. And so high temperature means intermolecular forces, which causes the molecules to become sticky, are less significant. That was the factor A of the Van der Waals equation. For an ideal gas, A is 0. There's no stickiness. Ideal gases don't stick to one another. The particles don't stick to one another. And the less ideal, the more sticky they are. Not only that, the more concentrated they are in terms of moles per volume. The more concentrated they are, the more likely they are to stick. And this is given as a square. And so this is the Van der Waals correction here for gases. So Van der Waals is interested in real gases versus ideal. So Van der Waals forces are these forces of attraction that cause the particles to be sticky. The other factor that causes ideal gases to deviate from real gases is ideal gases have 0 particle volume. And the volume of the particle themselves is negligible. So if you have 1 meter of gas, it's 1 meter of empty space, but it really isn't 1 meter of empty space. The particles themselves are going to occupy some of that 1 meter. And so we actually have less than 1 meter. The bigger the particles are, the less empty space there is, which increases the pressure. But that term is not shown here. That's not the Van der Waals force. And so let's take a look at the Van der Waals forces or the IMFs. We're not going to start with dipole and polarizability. Dipole moments are given by mu. You can measure those. And the units for mu are dpi. We're going to start off with not dipole. We're going to start off with instantaneous induced dipole. Instantaneous induced dipole, that's a long name. For what type of IMF? This is a short name for this, instantaneous and induced. What instantaneous and induced is, you take a non-polar. So over time, the average, the electron is in this cloud, but in one instant of time, the electron might be on the left side. The electron's on the left side, the right side's going to be positive, and the left side's going to be negative. That's an instantaneous dipole, but that instantaneous dipole in the next second is going to disappear because the electron's constantly moving. It's not frozen here. Eventually it'll be over here, over there. And so over time, it's non-polar like that. In one instant of time, it could be polar like this. Polar dipole would have 2 poles, positive pole and negative pole here. What that instantaneous dipole is going to do is it's going to induce dipole. So if this green one, which is neutral, sees this negative, then the electron is going to go to the opposite end. This negative and negative repel. And so if the electron goes to the opposite end, then it's going to induce a dipole here. Now, this instantaneous induced dipole, the attraction here between these two particles lasts only for a moment. The next moment of time, it disappears. But when we average it over a whole bunch, of instantaneous induced, they're fleeting, but net they're going to result in an attraction. And this attraction is called, we don't usually call it instantaneous induced dipole attraction. We call it what? Well, there are multiple names that it's called, and it's dynamic. Sure, dynamic. And we call it dispersion or London. And so these are London forces here, dispersion. Both of those They're used interchangeably. Okay, so the more electrons we have, the more attraction we can generate between these. So if we look at helium, helium has 2 protons and 2 electrons. So time average, those electrons are moving around. And so over time, this looks pretty symmetric and neutral. In one instant of time, we could have both electrons on the same side. They aren't going to stay there continuously, but this is going to lead to something that's more lopsided. And so this will be our instantaneous dipole here. And that can induce a dipole in an adjacent helium, and then we'll get an instantaneous induced dipole attraction. And so we can generate this. This is going to be lopsided now. There's going to be a delta negative end and a delta positive end. And therefore, if we have another helium next to it, that helium is going to see the positive end, and therefore both electrons are going to be attracted to it. And it's going to induce a dipole here. If we compare that to something like xenon, helium has a total of two electrons. Xenon has a total of 54 electrons. So if we compare this to xenon, xenon's going to have 54 protons in the nucleus. And over time, it's neutral. But let's say all 54 electrons decided to move to the left side. If all 54 electrons decided to move to the left side, then we're going to generate a huge instantaneous dipole. This would be extreme. You wouldn't expect all 54 electrons to end up here on the left side. So we've got 54 protons, and let's say all 54 electrons come here. We're going to generate an enormous instantaneous dipole. And the probability of that is kind of low, or maybe an extra electron moves over here. But this instantaneous dipole is going to be much, much bigger. And so the more electrons we have, the larger the instantaneous dipole. And so what we can say is the more electrons we have, the more we can polarize the electron cloud. Polarize is to distort the electron cloud. This versus this. The fewer electrons we have, the less polarizable. And so this is much more polarizable. Polarizability. This has much smaller polarizability. And therefore, xenons are a lot more sticky than heliums. And so what we do is we use temperature as a gauge for this, and we use something like boiling point. So if you wanted to liquefy helium, that is slow it down so that they can stick to one another, you have to cool the helium down to 4 Kelvin. At 4 Kelvin, the helium atoms are moving slow enough that they can stick to each other. When they stick to each other, they liquefy. Xenon, you don't have to cool it nearly as much. You can use boiling point to tell us this. And so if we go over here and just look up the boiling point for xenon, we expect the boiling point for xenon to be much higher because the atoms are a lot stickier. Since the atoms are a lot stickier than And let's see what we have to cool it down to. So here's xenon. We just have to cool it down to 165 Kelvin. Helium, we have to cool down to 4 Kelvin to get the atoms to stick together. Xenon, we cool it down to 165 Kelvin, and then the atoms will stick together and liquefy. And xenon's much more polarizable. Therefore, it's expected to have much stronger dipole, instantaneous induced dipole, or much stronger London, or much stronger dispersion forces, and a much higher boiling point. Or the reverse of boiling is condensation, And so it either boils or condenses at the temperature. All right, so London forces increase with more electrons. Your book doesn't count the electrons though. What your book does is they don't look, it's really the number of electrons that dictates the polarizability. But what your book does is, rather than using the number of electrons, it uses the molar mass. When we think about molar mass, why use molar mass? Well, a lot of people will calculate the molar mass stuff rather than count up how many electrons. So you can easily look it up. If you want the molar mass of carbon tetrachloride, just look it up on Wikipedia. It's 153. Versus if you want the number of electrons in carbon tetrachloride, then you're going to have to look at the periodic table and calculate. This is a total number of electrons, not valence. So the total number of electrons on carbon is 6. Out of the 6 electrons, 4 are valence. In chlorine, the valence electrons are 7, but the total number is 17. And so we add up all the electrons, and then we can see. And so the molar mass is proportional to the number of electrons, and therefore, it gives us a means. I like number of electrons because sometimes 2 molecules will have the same number of electrons, but slightly different molar mass. And then we have the polarizability here. The quantitative. This is something you can calculate using quantum mechanics. Polarizability is referred to as a polarizability problem, so that's cubic centimeters. These are from the CRC. And then we can see, okay, so the greater the polarizability, the greater the number of electrons, the stronger the dispersion forces, the higher the boiling point. And so these are the stickiest. So the stickiest of these will be carbon tetrachloride. Now, one thing about all these is that's the only attractive force holding these together. Carbon tetrachloride is what we call nonpolar. Propane is nonpolar, because carbon-carbon bonds are nonpolar and carbon-hydrogen bonds are nonpolar. And chlorine is nonpolar, ethane is nonpolar, methane is nonpolar, nitrogen, oxygen, hydrogen are all nonpolar. And so it's the number of electrons. Okay. Okay, so we'll take a look at some other nonpolar species. Here, methane's nonpolar because the bonds are nonpolar. Let me take that back. They're just very slightly polar. They're not polar enough. So this is tetrahedral. Silicon tetrahydride is going to be slightly more. This is silane, this is methane, silane. Is slightly more electronegative. Is it silicon? Yeah. Or no, slightly less. But it doesn't matter, even if it has polar bonds, you know, these bonds are going to be a little bit more polar. Even though it has polar bonds, the polar bonds cancel one another because of its shape. So let's take a look at this show. You know. So whenever we have it, you know, the bond dipole can be pointed either out or in, depending on which one's more electronegative. Let's say they're pointing out. Okay, when we add these four bond dipoles in 3 dimensions, we get the molecular dipole. The molecular dipole, the sum of those bond dipoles, in this case, will be 0. And so this is non-polar. All the bond dipoles cancel. That's the spherical symmetry of tetrahedral geometry. And so what we're looking at then is if it's non-polar, then what we're looking for instantaneous dipoles. If we're looking for instantaneous dipoles, which one is going to generate the largest instantaneous dipole, potentially? The one with the most electrons. And rather than figuring out how many electrons we have, we're just going to use the molar mass as a proxy for a number of electrons here. And so the higher the molar mass, the more electrons we expect. And so when we look at this series, it makes sense. Methane has 10 electrons. Silane, okay, silicon has 18 electrons. Germanium has 36 electrons. And finally, tin tetrahydride or stannane is going to have 54 electrons. Yeah. And so this has by far the most electrons, and therefore it's going to have the strongest dispersion. And then we can look at the boiling point. The stickier the molecules are, the higher the boiling point. So tin is the stickiest. Okay, so the instantaneous induced dipoles what we talk about first. Next, we're going to talk about dipole-dipole interactions. Dipole-dipole interactions are between polar molecules. And these are going to have permanent dipoles. So let's take a look at HCl. HCl, chlorine's more electronegative than hydrogen. And so we're going to set up a dipole like this. When we add up the bond dipoles, well, the bond dipole is going to equal the molecular dipole. The dipoles we can actually measure or calculate. We can measure them experimentally or calculate them quantum mechanically, and we can get the dipole moment. The dipole moment is given by the symbol mu, and it's in Debye. We're not going to do anything with it. So this is the permanent dipole. Okay, let's compare HCl HBr. HI. We're going to look in terms of molar mass and the boiling point here. HBr, bromine is less electronegative. If bromine is less electronegative, then we expect a smaller dipole. And then iodine is even less electronegative than bromine. And then we expect an even smaller dipole. So these aren't instantaneous, these are permanent dipoles averaged over time. And dipole-dipole attractions are going to be permanent dipole attractions. And so which one will have the strongest dipole-dipole attraction will be the one with the greatest. And so if I think about it, HCl should have the strongest dipole-dipole attraction. That is, the delta minus here is going to be attracted with delta plus here. Delta minus. There are two poles, positive pole and negative pole. And so this is our dipole-dipole attraction. HI should have the weakest dipole-dipole attraction. But what's happening here is this. What's happening here is we see we're having decreasing dipole attraction as we're going left to right. And therefore, if we're having decreasing dipole, we expect the boiling point to go down. But what's happening with the boiling point? It's going up. And so something's wrong here. Because we expect the opposite. And so let's see what's wrong here. What's wrong here is this. Chlorine has 17 electrons total. With hydrogen's 1, it gives us 18 electrons. Bromine has 35, plus hydrogens is 36. Iodine has 53, plus hydrogens gives us 54. And so we end up with 18 electrons here, 36 electrons here, 54 electrons here. So which one is more polarizable? HI. And so HI is the most polarizable. And so what's happening here is as we're going left to right, we're getting increasing polarizability. As we have an increasing number of electrons. which means increasing London forces or dispersion forces, which is going to result in increasing boiling point. So what must be happening here is we have two competing things. On the one hand, dipole tells us the boiling point should be going down, left to right. On the other hand, polarizability, or London forces, is telling us that boiling point should be increasing. Now, which of these two are dominant? Which of the two are dominant is, it's got to be due to polarizability. That's it. Distortion of the electron cloud. And so how do we visualize something like this? How we visualize something like this is like this. When we look at HCl, we look at two things. We look at its permanent dipole. The permanent dipole is fixed on this. And then we look at its instantaneous dipole. Its instantaneous dipole is going to be based on having 18 electrons. And so this is the permanent dipole. The permanent dipole is the average, time average. If we compare that to the instantaneous dipole, based on a total of 18 electrons, we're going to say it could be very small or much bigger. So if all electrons go to one side, let's say these two bonding electrons go to the opposite side of the chlorine, we're going to get a bigger one. And so the instantaneous dipole is going to fluctuate between very small and quite big. And so we have these fluctuating instantaneous dipoles, which is going to generate a London force. And so what that means is London forces are dominant here because that's what's observed experimentally. Experimentally, London force is dominant. And how do they dominate? Well, how they dominate is we compare HCl with HI. HI is going to have a much smaller permanent dipole because iodine is less electronegative. And so the permanent dipole is quite small. However, when we look at the instantaneous dipole, iodine has 53, 54 electrons, HI. And therefore, with 54 electrons, the instantaneous dipole could be quite small, or it could fluctuate to quite big. And so in the case for HI, we can get much larger instantaneous dipoles, and this is fluctuating. Over time, the average comes out to that. And so because of these large fluctuations in the dipole here, HI is going to have stronger attractions. Not due to the permanent dipole, but due to these fluctuations in the magnitude of the dipole. And so this is what accounts for London dominating here, because the instantaneous dipoles you can generate with HI are much bigger than the instantaneous dipoles that you can generate with HCl because of the high polarizability of having 54 electrons. Versus 18 electrons. Are we out of time? How did I run out of time? I didn't even make it very far, unfortunately. I needed to get through this, but it's okay. Well, we'll continue this on Thursday. Going slow.